We could have worked out the direction of acceleration by combining the vectors of tangential velocity about a circle to form a vector triangle. Subtracting the tangents of all the velocities around a circle always ends up giving an overall vector pointing towards the centre of the circle. Working out the size of the vector requires mathematics which is beyond the scope of most A-level specifications, so isn't included here. However, in the same way you can infer that the size of the centripetal acceleration is inversely proportional to the radius of the circle, you can also infer that the acceleration is directly proportional to the tangential velocity squared. Centripetal acceleration is the combination of angular speed and tangential velocity. It is equal to angular speed multiplied by tangential velocity. The faster an object is travelling, the greater its tangential velocity. If you keep the radius of your circle the same, then an increase in tangential velocity also increases the angular speed. The multiplication of these two measures of speed gives us the value of our acceleration. The greater the change in either one, the greater the change in acceleration. Acceleration in terms of angular speed is given by acceleration equals angular speed squared multiplied by the radius of the circle. You simply express tangential velocity as 2 pi rf and replace 2 pi f with omega. Omega, the angular speed, equals 2 pi f, and tangential velocity equals 2 pi fr, where r is radius and f is the frequency. This means that acceleration is 2 pi fr times 2 pi f, which equals 4 pi f squared r, or omega squared r, where omega is angular speed. Reversing the process and expressing angular speed as 2 pi f, you have 4 pi squared r again. Tangential velocity squared is 4 pi squared r squared. If you divide tangential velocity by the radius r, you get an equation for acceleration as v squared divided by r, where v is tangential velocity and r is the radius.